Some special cases regarding Newton's second law. First of all, ramps. When there is a ramp, remember that the free body diagram is going to be drawn first. The normal force is perpendicular to the surface. To draw that component triangle, we're going to continue the normal force into the ramp, dotted line into the ramp, and then connect that dotted line to our weight force vector. The angle between the weight force and that normal force continuation line is going to be the same angle that the ramp is at. From here, we're going to do our Newton's second law, stuff that makes it go minus stuff holding it back, parallel to the ramp and perpendicular to the ramp. Normally when we do parallel, the stuff that's making it go is going to be mg sine theta, and the stuff going perpendicular is going to be the normal force, mg cosine theta. Down the ramp is going to be frictional force, mu times normal force, or mg cosine theta, and so on. The coefficient of friction can be found using tan theta, because sine over cosine equals tan. Do that derivation, check it out, make sure you can do it. Remember that different situations are going to be represented with different scenarios, and you're not going to get the same question that you saw this entire year. For instance, a skier on a hill is the same thing as a block on a frictionless ramp. So treat it the same way. Doesn't matter about what you're actually looking at. It does to kind of see it in your head. Remember to mentally picture these scenarios because you understand physics better than you think you do. Or a bird flying could be the same thing as driving a car. A drag force or resistive force are in opposite direction of acceleration for your free body diagram. Differential equations in physics C may show up here, like negative kx equals m dv dt. For these, that's not a great example because it should be m times d squared x over dt squared, so that we have x terms. That's also a differential equation. But here, remember to use separation of variables for differential equations. Use substitution if necessary. And then we're going to integrate both sides with our correct bounds. Circular motion. To move in a circle, there has to be a tangential speed and a centripetal acceleration towards the center of the circle. Centripetal means center seeking. So the acceleration towards the center of the circle would be centripetal. However, there may also be tangential acceleration, which means we're slowing up, slowing down, or speeding up, and centripetal acceleration at the same time. Like in elliptical orbits, remember to add your tangential acceleration with your centripetal acceleration using vector addition to find out where the total acceleration is going to be if there is in fact both. In a circle or part of a circle, the net force directed towards the center is the centripetal force. So we use the forces going in minus the forces going out equals mass times our centripetal acceleration. Remember, there's two forms of centripetal acceleration that could be useful, v squared over r or omega squared times r. The centripetal force will never be on a free body diagram, just like the net force will never be on a free body diagram. Period is the time it takes for one cycle. Frequency is the inverse of the period. So frequency equals 1 over period. Angular frequency is the number of circles per second. Omega equals 2 pi, because if we go completely in one circle, we've gone 2 pi radians divided by our period. For Atwood's machines, if you've got two objects, have two free body diagrams and two Newton's second law equations. Or if you're treating the whole thing as a system, one object, one free body diagram, one net force, and one acceleration, because they're going to accelerate at the same time. If you have three objects, then you're going to have three free body diagrams, and so on. For gravitation, you're probably going to be comparing a new planet to some other planet, so write the equation twice, whether it's the gravitational field equation, little g equals big G m over r squared, or the Newton's universal law of gravitation, F sub big G equals big G m1 m2 over r squared. Don't forget that r squared. Gravitational field equation, again, there it is, for any of our gravitational field calculations, should there be any, we're just going to use 10. That using of 10 means we don't really have to worry about significant figures. Okay, so don't stress out about that. Inside a spherical body, sorry, chemistry teachers. Inside a spherical body, planets, stars, asteroids, whatever, there's going to be zero net force because you have a gravitational force pulling in every single direction because there's mass above you and below you and to the left of you and to the right of you.